Welcome to our presentation of the Space Debris Deorbiter project that is sponsored by Edgar Herrera from the Aerospace Corporation and with advisement from Ted Nye. My name is Emily Silva, and I will now present an introduction and a background. Space is an environment with some gravity that allows objects to go in orbit. Many objects may be found orbiting the Earth besides the Moon. The illustration on the left is debris that are objects left behind in space over time. The debris may range in size, including pieces of paint, fragments of satellites themselves, and fragments created by explosions or collisions. The illustration on the right has small satellites, where one U size consists of length, width, and height, each being 10 centimeters. A 1U small satellite may be configured into 2U, 3U, 6U, and 12U as shown here, and many other configurations. So within low Earth orbit, there is a lot of debris concentrated as illustrated on the left image. Low Earth orbit is a range of altitudes from the surface of the Earth up to around 2,000 kilometers. And as shown on the left, on the right, the number of total objects has increased up to now. Two collisions are pointed out in which the amount of debris in low Earth orbit increased within a short amount of time. The objective was to develop a small satellite that is capable of capturing and deorbiting debris from low Earth orbit. We had several requirements. Most of these were met with the exception of the number of debris that may be deorbited. And now I'll introduce Maya, who will present system engineering and overview.
Thank you for the introduction, Emily. So to determine where our debris deorbiter would be most needed, we looked into the debris density at different altitudes and orbital inclinations. So in the graph on the left, we can see a graph of debris density at different altitudes. And from this graph, we can see that the highest density of debris is between around 700 to 1,000 kilometers of altitude, which is the area that we decided to target. Then on the right, we can look at different debris distributions at different orbital inclinations. And as seen in the figure on the top right, the orbital inclination describes the angle at which a satellite orbits around the Earth, where a 0-degree orbit goes around the Earth's equator in an equatorial orbit, and a 90-degree orbit goes around the poles in a polar orbit. Then in the graphs below, we show the debris distribution data from two different data sets, which show the debris distribution over different inclinations. And from this, we can see that overall the debris is relatively spread out over different inclinations, but it tends to be around the 30 to 90 degree inclination range. So next, this is a diagram of our mission overview, which shows the different components involved in the overall mission. So in the center here, we have our satellite, which is the debris capture satellite, which communicates with a ground communications receiver on Earth. And this ground communications receiver will be able to monitor and control our satellite. Then lastly, we have our piece of debris, which is what we're hoping to capture and deorbit back to Earth. Next, we have our concept of operations, which lays out the steps that we take throughout our mission. So first, we start by our satellite being dropped off by a rocket, hopefully near debris. Then our satellite will approach and align with a piece of debris and use its sensors to analyze the debris's position and location. And then from there, we will deploy a weighted boom and then attempt to maneuver closer to the debris and capture it. And we will also be communicating with mission operations to determine the success of this operation. Then lastly, once we have our debris, we will deploy our deorbit method and determine the success of the deorbit. So as we were designing our satellite, we used simulations in MATLAB Simscape throughout the design process to make sure it would be able to operate under collision conditions. Through the simulation process, we decided to use a 10-meter long weighted boom, which allows us to collide with debris without spinning out of control and exceeding our star tracker sensor's maximum spin rate, which is 0.6 degrees per second. So using the weighted boom, we're able to capture debris at collision speeds of up to 5.3 meters per second, which is around 11.9 miles per hour, as we can see in the simulation here. Next, Victor will be talking about the spacecraft design.
Thank you, Maya, for the introduction. So now that we understand the problem and our plan to solve it, let's take a look at our spacecraft. So here you can see our spacecraft deployed. Here's our deorbiter in its deployed form. On the left, you can see the size of our craft. We're about 340 millimeters long, 214 millimeters wide, and 214 millimeters tall as well. You can also see our mechanism for capturing debris on the left. Now on the right, you can see our antennas, our delta V thruster, and our solar panels, and some of the other components that we have on our craft. Next slide, please. Okay, so this is how we would have our spacecraft as it deploys from our dispenser. On the left, you have our spacecraft in the stowed configuration. That's how it would look while it's containing the dispenser that is used to launch us off the main launch vehicle. It does so with some internal springs you can see on the picture on the right. And as soon as the doors open on the dispenser, we are sprung out and ready to begin our mission. Next slide, please. Now let's take a look under the hood of our spacecraft. So here on the left side, you can see our propulsion system and our fuel tank, as well as our power and battery systems. On the right, you can see our electrodynamic tethers and our communication and data handling systems. Okay, next slide, please. So throughout this spacecraft design, we had mass and power requirements to meet. So these are very important in the field of aerospace. So when we were looking at our power budget, we found that we only needed 48 watts of power, which is well within our capabilities. And our mass only turned out to be about 22.8 kilograms. That includes our contingencies, and it allowed us to stay within our requirements as well. Next, please. So now we're going to have James talk a little bit more about the debris capture system.
All right, thanks, Victor. The capture mechanism was chosen based on a rigorous trade study performed in the first semester. As we can see here, 6 variations were chosen on compared based on various qualifying factors. It was clear from this effort that some version of a rigid net structure, which we dubbed a catcher's mitt, would prove to be the superior choice due to low power requirement, large capture volume, and a small stowed volume, and additionally a relatively small weight. So next slide, please. Here we see some of the detailed figures of our catcher's mitt design. Maya described in the results from some simulations regarding spin, which dictated roughly the size and orientation of our net. The goal was to get a large capture volume without creating a serious moment on the craft during capture. The left figure shows dimensions of the capture area and the 4 sets of carbon fiber arms. Those are in red there. The components extending from the tops of the arms serve as doors effectively and are opened after deployment, but closed after the object is captured. The right figure shows a top view with the doors closed. A camera, which isn't pictured here, is actually located in the center area, the center of the capture area on the bottom of the net. Next slide, please. Here we see the stowed state of the capture device. We can see how the 4 sets of arms fold in on themselves in the right figure. Though not pictured, the net folds in as well with the arms. The volume of the storage area was calculated to include the net and the arms as well. The advantage of the folded arms is that the capture mechanism does not require much of the spacecraft volume, which was a limiting factor for us in the design. The net is made from an elastometric matrix graphite composite, which will prove to have an advantage in the deployment, which will be discussed in the next slide. Here, the capture mechanism is powered by a passive spring deployment system. Springs were modeled at each of the hinges on the arms in SolidWorks. The forces on the springs were estimated in order to develop a minimum torque requirement to deploy the arms. From this, a spring constant was calculated. It was found from simulation that it was most effective to use a common spring constant at all the hinges, which we came up with in this table here. This spring constant actually gave us an estimated torque of roughly 0.72 meters, which gave us a 2x margin on our torque. The doors pictured on the bottom left there are actuated by nitinol shape memory alloy wires. This proved a low power, reliable option to closing the cage once the debris is captured. The SMA actuator is a wire which current is run through, which changes the shape of the wire, and that is how we decided to close the doors after the object is captured. And next slide. All right, next up, Gustavo will be discussing our Deorbit system.
All right, thank you for that, Jimmy. So here we have the Deorbit method trade table that has been created in order to figure out which Deorbit method would be best fit for to be used on our CubeSat. Every method has colors that show blue representing the best and red representing the worst. We see here that electrodynamic tethered and drag sails are the top 2 choices for Deorbit based on the colors, but we ended up choosing the electrodynamic tether because it is lighter and smaller. Next slide. This slide shows the CubeSat along with the deployed electrodynamic tether. The force responsible for deorbiting the CubeSat is called the Lorentz force, which is the force exerted on a current carrying the conductor in a magnetic field. The governing equation for the Lorentz force is shown on the left-hand side and depends on the current, the tether length, the magnetic field, and the angle theta between the magnetic field and the current. This current is generated when the free electrons in the tether move from top to bottom due to their motion relative to Earth's magnetic field, as shown on the diagram. In order to maintain a flow of electrons in the tether, the electrons that approach the end mass will have to be emitted into the ionosphere through both thermionic and photoelectric effects. This makes the top of the tether more positively charged, which attracts electrons from the ionospheric plasma to complete the circuit. The interaction between this current and the geomagnetic field is what creates a Lorentz force acting on the tether opposite to its direction of motion. This Lorentz force, with the addition of drag, helps slow the CubeSat down, which decreases its altitude. Next slide. Okay, so here we see the Deorbit subsystem, which shows the stowed configuration on the left and the deployed configuration on the right. In the stowed configuration, the tether is in an accordion fold with the subsystem dimensions being 200 millimeters long, 100 millimeters wide, and 26 millimeters thick, and a total volume of 0.9 U. In its fully deployed configuration, the tether measures a total of 100 meters in length, with the end mass pointing toward Earth. So the way the tether deploys is once the mission is at its end of life, a signal is sent to the actuators to start the deployment process, which begins by powering the linear actuators. The linear actuators push the pins, rotating it away from the pin supports, which unlocks the end mass from the cap, therefore allowing the force springs to exert a force on the end mass to accelerate away from the CubeSat. Next slide. This slide shows the simulation results obtained from a program that simulates orbital decay using electrodynamic tethers. Looking at the graph shows 3 lines for 3 different inclination angles, which shows the time it took to deorbit from 800 kilometers to 350 kilometers. As we can see, at 0 degrees inclination, it took only 3 years to deorbit, while taking 60 degrees, 8.2 years, and 80 degrees, 16.2 years. Per requirement, as shown on the vertical dashed red line on the graph, the CubeSat must deorbit within 25 years of its end of life from low Earth orbit. And this data shows that there is enough margin to specify this at orbits between 0 and 80-degree inclination angles. Next slide. Thank you. And now my teammate Jasmine will be presenting the propulsion system.
Thank you, Gustavo, for the introduction. In order to complete our mission, our SmallSat's propulsion system must be able to perform two functions. One is that it must be able to perform major delta V movement. This will allow our SmallSat to have large altitude changes. So as you can see in the green box, this is the major delta V simulation. This function will be used for large altitude changes when we move from one target to another. The second function is that our propulsion system must be able to perform rendezvous proximity operations and docking, RPOD. This will allow our SmallSat to orient itself when capturing debris. In the purple boxes, one can see the RPOD simulations. So our SmallSat has 6 degrees of freedom. It has X, Y, and Z translational motion capabilities, as well as roll, pitch, and yaw motion capabilities. For the sake of time, we're only showing the translational motion along the Z-axis and pitch motion along Y-axis. Next slide. So we have a hybrid design for our propulsion system. So we have a cold gas propellant, which is used for the RPOD function, and a green propellant, which is used for the major delta V function. So if we look at the CAD, the blue control box is the modified Marco MIPS. Inside this control box is the cold gas propellant tank. The Marco MIPS has 12 reaction control system, 25 millinewton thrusters. So there's 2 thrusters on each face of our SmallSat. For the ECAP system, the green propellant tank is in the center of our SmallSat, and the ECAPS has a 1 Newton HPGP thruster in the center. Next slide. So here we have the propulsion system schematics. On the left side, we have the ECAP schematics. The ECAP specifically uses LMP103S propellant. This is a type of green propellant. On the right side, we have the Marco MIP schematic, and this one uses the R236FA cold gas propellant. This wraps up the propulsion section. Next slide. Now Emily will be concluding our presentation.
Now, although capturing and deorbiting debris is a difficult endeavor, the team designed a 12U SmallSat that meets almost all project requirements. Additionally, the team gained exposure to design and simulation tools, including MSC, SolidWorks, and Simscape. Lastly, the team coordinated remotely and delivered a project.